Hello everyone, I am Aswani, Assistant Professor, Department of AIML at MLR Institute of Technology. Welcome back another session of Artificial Intelligence. In today's session, we are going to learn about multi-layer feed-forward networks. In the previous sessions, we already started artificial neural networks. We have seen the introduction part, what is artificial neural networks, how it will be constructed, how the human made that artificial neural network, how and what are the structures. There are three types of structures we have seen. Already we have completed single layer feed forward network. In that it consists of input layer and output layer. Input layer forward the information to the output layer, and it will be weighted sum up, and there are some activation functions are there. Based upon the scenario, we will choose one of the activation function to decide the output. Okay, in this session we will learn the multi-layer feed-forward networks introduction, XR example. In the single layer feed-forward network, it will solve the linear separable problems only. For example, and R function problems, and here multi-layer feed-forward networks will solve the non-separability problems. So non-linearity. Here we'll see the XOR example and backpropagation training algorithm also. Okay, let's start introduction part of multi-layer feed-forward network. So what is the purpose of multi-layer feed-forward network? Is handle data that is not linearly separable. The linearly separable means drawing the straight line to categorize the categories. For example, C1 and C2, there are two categories. To separate this C1 one side and C2 another side, we are able to draw the straight line, hyperplane. Then that kind of problems are called as linearly separable. If you are unable to draw the hyperplane or straight line, then we will say that as not linearly separable. So the architecture of multi-layer feed-forward network is, it consists of input layer, hidden layers, and output layer. So here the input layer directly can't forward the information to the output layer. There is a middle layer called hidden layer, which will process the information. After that, from the hidden layer to it will forward information to the output layer. After that, it will decide the task, or which will categorize the output. Okay, so each link from input to hidden layer and hidden layer to output, it consists of the weight, each link associated with the weight. Okay, let's see the training process of each layer. So how it will calculate the error? So first, compare the network's output to the correct answer using a predefined error function. So here whatever computed error is there and actual error, then it will observe that error and it will take that error, and to adjust that to minimize that error, we need to adjust the weights using backpropagation. Adjust weights based on the error, which we need to minimize that. Next, repetition. Repeat the process over many cycles until error is negligible, indicating the network has learned the target function. So how many times we need to repeat the same process means here unless the error negligible. For example, 0.01, then we can stop doing the same process. Okay, let's see the architecture. Here, input layer, hidden layer, output layer. So here 2 for 2 feed forward networks are 2 input nodes, 4 hidden nodes, and 2 output nodes. The architecture is input layer, hidden layer, output layer. Each layer, each node will have the connection with another node, and which associated with the weight. In the each and every link will be associated with the weight value. Here there are two approaches how we can minimize the error: gradient descent, the general method, and another one algorithm is backpropagation algorithm. Let's see the gradient descent method. So which is a generalized method, is applied in case of non-linear classification for proper adjustments of weights. So It is used for nonlinear classification. Adjust weights by determining derivative of the error function. Derivative will use the derivatives and will minimize the error with respect to the network weights to minimize the error. In the gradient descent, we'll use the derivatives of the error with respect to the network weights to minimize the error. That is the generalized method to adjust the weights and to get the proper output. The next one is back propagation algorithm. So it is applicable only to network with differential activation functions. A typical example of nonlinear separable is the XOR function. We will see. Okay. So XOR function, the inputs we know already. This is a Boolean table, logical values x1 and x2, x1 XOR x2. If the values are same, then we'll get the 0, otherwise we'll get the ones. 0 0 then 0, 1 1 then 0. If the input values are 0 1 1 1 0 1 is the output. So for this XOR function, the graph is, we can't draw a single straight line to separate the values. Here look at this one graph, true false false true. We can't draw a single line here. Anywhere we can't draw the single line to separate the false false and true true. So it is called as non-linear separable problems. Linear separable means to separate the true and false values, we can draw the single line, for example and R functions. Okay. So from the above graph, we can see that no single line can be drawn separate the false and true into distinct classes. Therefore, function is said to be non-separable. For such problems, feed-forward neural network is used to hidden nodes and it makes use of the sign function, step function. So here the activation function is pi of V induced field. If V is less than or equal to threshold theta, then the value is 0, otherwise the value is 1. Okay. So here the architecture for XOR is feed-forward network, neural network for XOR is, there are 2 nodes, 2 input nodes, 2 hidden nodes and 1 output node. Let's see. So x1 to x2 input values, so 0, 0, 0, 1, 1, 0, 1, 1 are the input values and these are the weights. From x1 to h1, 1 is the weight, from x1 to h2 minus 1 respectively. From x2 to h1, x2 to h2, the weight values are minus 1 comma 1. From hidden nodes to output layer, the weights are 1 and here there is a bias, that is minus 0.5, which is also need to be added in this function. Okay, let's see. The connection from input nodes to hidden nodes are weighted with the weight vectors 1 comma minus 1 and minus 1 comma 1, indicating weights from x1 to h1, x1 to h2. The weight on connection from hidden to output nodes are 1. The output node is used to combine the outputs of 2 hidden nodes and the bias negative fraction is minus 0.5. Okay, let's see the tabular format. Inputs x1 and x2, output of hidden nodes h1 and h2, output nodes and x1 XOR x2. So for 0, 0 input, what is the output value? So here the weight value is 1 comma minus 1, minus 1 comma 1 are the values. For 0, 0, 0 into 1 plus minus 1 into 1, then it is 0. In the similar way, 0 into minus 1 plus 1 into 0. 0 is the output. In the similar way, we need to apply all the training examples, then we'll get this output. And here we need to apply the step function, that is if V is less than or equal to theta, then it is 0, otherwise it is 1. So here we applied the same formula and again we have to calculate the output node values from hidden nodes to output nodes. Here why minus 0.5? Because it is the bias value. So 1 is the output value, is whatever the values 0, 0. 1 is the output, 0 into 1 plus 0 into 1, then it is 0 plus minus 0.5 because it is the bias value. So we'll get the minus 0.5. After applying the step function, we'll reach with the decision of 0. And again, 0, 1, 1, 1 are the weights. So we'll get 1 is the output, where 1 is the 1 plus minus 0.5, then we'll get 0.5 is the output. Then after applying the activation function, we'll reach this 1 as the output. So after that, x1 xor x2, the output is 0, 1, 1, 0. Okay, so let's see the same calculation for H1. W11 equal to 1, W21 equal to minus 1. For H2, W12 equal to minus 1, W22 equal to 1. We can use these weights to verify the output of the hidden nodes H1 and H2. The calculation of H1, H2 is rectified linear unit. We applied the activation function, and here for this the values are max of 0, x, max of, for example, 0, 1. Then the value is 1 is the output. So we have applied these formulas to find out how it will be work. So for each input 0, 0, the values are 0, 0. Input 0, 1, the values are 0, 1. Input 1, 0, the values are 1, 1, 0. Input 1, 1, the values are 0, 0. Next, similarly, hidden nodes to output nodes. Input 0, 0, 0, 0, 1, 1. Input 1, 0, output node is 1. Input 1, 1, output node is 0. Okay. Let's see the back propagation training algorithm. So the existing feed-forward neural network is based on the gradient descent method. According to this method, the activation function used in feed-forward neural networks have to continuous function of the weights differentiable everywhere. So each and every training example, it will be differentiable. A typical activation function used in this case is the sigmoid function, which can be considered to continuous approximation of step function. So the activation function here is pi of vi equal to 1 by 1 plus e to the power of minus a into vi, where a is the learning rate, v is the induced field, that is weighted sum up. So here a is greater than 0, vi equal to sigma wij into yj, such that wij is the weight of the link from node I to j, and yj is the output node of the j. Okay, so the backpropagation algorithm learns the same of the single layer perceptron. Using a set of training examples, it determines those weights for which the total error of the network is minimum. So here backpropagation consists of repeated application of the two phases. One is a forward pass and second one is backward pass. How we have done in the single layer perceptron, we'll do the same in the forward pass from the input node to hidden node to output node. After reaching to the output node, we'll compare the computed output and desired output. If there is any error is there, again we'll apply the backward pass from the output node to hidden node to input node. Again we'll do the forward pass. In this, let's see the backward pass. In this step, the network error is used for updating the weights. So from the output node to hidden node to input node, and propagated from last node to start node. Let's see the figure here. Here, straight line, solid line shows that network activation for forward pass. It will start from the input to hidden to output. The dashed line shows that error propagation backward, output node to hidden node to input node. Okay. So the most training algorithms follow the same cycle. Let's see what is that. Run a set of input variable values through the network using a random set of weights. Already we have seen that in the single layer feed-forward network. Compute the difference between the computed output and actual output values and average the error over the entire training cases. Propagate the error backward through the network and compute the gradient of the change in the error respect to changes in the weight values. Make adjustment to the weight values. Each cycle is called as epoch since the error information is propagated backward through the network. This type of training method is called as backward propagation. So here first we need to start with the input node and we need to use the gradient formula and we need to find out the hidden nodes values. After that, hidden to output node in the same way. After that, we need to compare with the values from the computed output value and the desired output value. If there is any error is there, then we need to backward pass, we need to apply backward propagation algorithm and adjust the weights to get the negligible error, to minimize the error. Okay, let us consider an example. A network with 3 layers. Assume that I represent a input, J represent a hidden, K represents the output layer. Let Wij refers to the weight of the connection between a node in the input layer and a node in the hidden layer J. The following formula is then used to derive the output value. Yj is equal to 1 by 1 plus e to the power of minus xi, where x equal to sigma I equal to 1 to n xi into wij minus theta j, where theta j is called the threshold for the node j and n is the number of inputs to the node j. Okay, let's see the algorithmic steps for a training. Initialize I equal to 1 and initialize w of I also randomly. While loop, stopping criteria is not satisfied. If I less than or equal I less than max iteration, then enter into the for each. Example, x is the training and d is the desired output. Run the network with input x and compute the output y. Update the weights in backward order, starting from those of the output to hidden to input, computed using the delta rule. We'll see in the next slide. After completion of this for, again we need to increment I value and again we need to repeat the same process each and every time. Whenever the error is negligible, we need to end the while. These are the algorithmic steps to follow the backpropagation algorithm. Next, weight updated rule. In backpropagation using gradient descent, weights are adjusted proportionally to the gradient of the error between actual and computed output. The weight W is updated using the following formula. Wji equal to, for example, output node to hidden node, the Ji equal to Wji plus delta Wji, where delta Wji equal to minus eta into derivation of d divided by derivation of Wji. Already we have seen the previously. The eta is the learning rate and d is the desired output and W is with respect to the weights, network weights. Eta is the learning rate in the range of 0.1 to 9. And what is the termination criteria here? To minimize the error. The algorithm iterates until sum of squared errors for all training data in epoch. Each iteration is below a predefined threshold, example 0.01. Then we can terminate the process. Next, what is the goal? The objective is to minimize the error function by reaching the global minimum and avoiding the local minima. In batch mode, weights are updated after processing all examples in a training set. Wji equal to Wji plus sigma delta Wji for x, where x denoted the training example. Okay, let's see what are the stopping criterion. Total mean squared error change and generalization based criterion. Let's see. Total mean squared error changes. Convergence is achieved when the absolute rate of change in the average squared error per epoch is sufficiently small, typically between 0.1 to 0.01. Then we can stop the iterations. Another way is generalization based criterion. For example, if you take a total mean squared error, if you are preparing for exams, if you know that, and if you are trying to learn the same thing multiple times but you are unable to learn that one, then we will neglect, we'll leave that question and we'll go to the another question. Okay, in the same way here, when we reach the 0.01 as the error value, and whenever we are doing the same, adjusting the weights, and again we are computing the output, we are reaching with the 0.01, we will neglect that one, we'll stop doing the process. Next, generalization based criterion. Here, for example, again the same example, if you are preparing the same, and if you reach you conducted yourself as a test and you reach some maximum marks, you got the some maximum marks, and again if you are preparing the same question, it is not useful, for example, because you already learned that question. So here also, generalization based criterion, you reached some error point. So to reach, for example, 0.01 already reached, if you want to correct that 0.01, it is no use to do. That is what generalization based criterion. After each epoch, the network is tested for generalization. If the performance is adequate, means stable, training stops. The test data used for this check does not contribute to weight updates. Okay, what is the delta rule for error minimization? The delta rule continuously adjusts weights to minimize the mean squared error, also known that least mean squared error. The process involves representing a training example of pair xi and desired output di for 1 less than or equal to I less than or equal to n, reducing the error between the actual and computed output. Let's see the algorithmic steps. Compute the error of output neuron k after the activation of the network on the ith training example xi comma di equal to error dk minus yk, means a desired output minus a computed output. Here yk is the output of the kth neuron. The network error is defined sum of the squared errors of the output neuron and is calculated as sigma ek ith neuron of the square. Here it is a square for kth output node. The total mean squared error is defined as average of the network error of the training example and is given as E equal to sigma I equal to 1 to n E divided by n. So E is the error value, n is the number of input values, training examples. Minimize the average error. Okay. In this session, we have seen what is the architecture of multi-layer feed-forward network. Next, we have seen the XOR. Next, we have seen the definition of gradient descent method. Next, we have seen the back propagation algorithm. Okay. So, how we can minimize the error? What are the stopping criterions we have seen in this session? In the next session, we'll see the radial basis function network. Thank you.